Hi guys, this is Module 9, Lecture Notes 18. Today we're going to dive a little bit deeper into some bonding. If you remember from our past lessons, there are two types of bonds, ionic and covalent. Remember, ionic is when you have a metal from this side bonding with a nonmetal, and the metal always just gives its electrons to the nonmetal. But today we're going to be looking a little bit deeper at covalent bonds. And covalent bonds always happen between nonmetals, okay? They all really want a few more electrons to be like the nearest noble gas. And so in order for everybody to be happy, remember in covalent bonding, they have to share electrons, okay? Just like when you share a cookie with a friend, or you share a toy with a sibling, do you think they share them completely equally? Okay, and the answer to that is no. When electrons are shared, it's kind of like a tug of war between two atoms. Okay, so we're going to look at two types of covalent bonds. Nonpolar covalent bonds or polar covalent bonds. And your book uses the term purely covalent. So the two types are nonpolar and polar. So let me give you two examples. If I have a fluorine sharing electrons with another fluorine, they are going to share the electrons equally, okay, because they're the same atom. So the tug of war is pretty equal in this case. This is nonpolar. In a polar covalent bond, you have two different types of elements trying to share electrons. And in this case, one of them is going to pull harder on that bond. They're going to pull the electrons more towards themselves in this tug of war. And you represent that with an arrow. Okay, I want you to write down that you're going to draw the arrow toward the element with a greater electronegativity. And we will talk about that, what that means in just a second. Okay, but from this section, all you need to know is that nonpolar means they're shared equal, and polar means they're shared unequally. One of them pulls a little bit harder. Okay, so let's look at this term electronegativity. Electronegativity is an element's tendency to want to gain more electrons. If something has a high electronegativity, it really wants more electrons. Remember, these guys over here, they really don't. They want to actually lose electrons. And so that's why as you move this direction on the periodic table, the tendency to want to gain more electrons increases. Okay, so let's define this out to the side. The tendency of an element to want to gain more electrons. Okay, notice that towards the right and towards the top of the periodic table, these elements have a high electronegativity. Okay, so I just wrote highest towards the right and to the top of the periodic table. These guys really, really, really want to gain more electrons, especially these group 7 elements. Okay, so let's use that to determine if a molecule is going to have polar or non-polar bonds in it. Remember when we're talking about the tug of war. So let's jump into an example, NH3. Okay, here's our rules. If it's a bond between two of the same atom, then you don't need to do anything special. It's nonpolar. But if a bond exists between two different atoms, it's polar. And you're going to have to decide which of those two elements has a greater pull, or which one has a higher electronegativity. And you can use this table to figure that out. Okay, so if I drew a picture of NH3, I would have N in the center. I'd have hydrogens bonded to it. And remember, I have an extra line. If you're not sure where my lines came from, you'll want to go back to the previous lectures and see how I added up the valence electrons and divided by 2 to figure out I'm allowed 4 lines in this picture. Okay, because we have two different elements, one of these is going to pull harder on this shared bond. Let's look at our table down here. Here's nitrogen and here's hydrogen. You can see that nitrogen has a higher electronegativity. So I need to show the electrons are being pulled by the nitrogen in this case. And that's how I would complete this picture. It has 3 polar bonds pulling towards the nitrogen. Okay, let's do CO2. I'm going to give you a second to draw your bonding picture. If you need to add up your electrons to the side, go ahead and do that. Bond it, look at your table, and decide which direction the electrons are going to be pulled. Over here, I added up my valence electrons. For carbon, 2 oxygens divided by 2, I'm allowed 8 lines in my picture. Carbon always goes in the center. I bond my oxygens. And remember, everybody has to have a full octet. So if you look at oxygen, carbon, and the other oxygen, everybody needs 4 lines touching them to fulfill their octet. So that's how I ended up with 2 double bonds. Now we need to decide in this tug of war between carbon and oxygen, who is going to pull harder on that bond. You come down here to your table and you look at the location of both of them. Whoever is further to the right into the top of the periodic table has a greater electronegativity. So in this case, the oxygens are going to pull harder on that bond. And you show that by drawing the arrows outward. Okay, so now that we know how to determine if individual bonds have polarity or not, we're going to draw a molecule as a whole, and we're going to assign one of these terms to the whole molecule. Is it polar, meaning it's asymmetrical or it's unbalanced? Or is it nonpolar? It's symmetrical, it's completely balanced, and all the tug of wars are equal. Okay, so these are really 2 terms that you need to be very familiar with from this lesson. I always think polar, unbalanced, nonpolar, balanced. Okay, so if we're going to do this from start to finish, I've written out a few steps for you here. The first step is to draw a flat picture of it, okay, and then we're going to assign arrows to each of the bonds. So let's do that in this case for CCl4. All right, so here's CCl4 with all of its electrons. We did step 1. Now we're going to determine the individual bonds, what we did in the last section. We're going to determine who pulls harder on this bond, this bond, this bond, and this bond. And you can quickly do that on your table by looking at where carbon is and where chlorine is. I would say in this case, because chlorine is so much further to the right, the chlorines are going to have a harder pull. They have a greater electronegativity. All right, so that's kind of review. Now we need to assign one of these terms to the whole molecule. Would you say that it is asymmetrical or symmetrical? When I look at this picture, I see somebody pulling up, somebody pulling down, somebody pulling left, and somebody pulling right. And it all pretty much cancels out. It is very symmetrical. And so I'm going to assign the term non-polar to this one. If you're a really visual person, you can think about what shape would that be that we learned from last week. This one would be tetrahedral. And if everybody is pulling equally on that center, then this is going to be non-polar. All right, I would like you guys to try the one right below it. Try CFCl3. All right, over here to the side, I've added up my valence electrons, and I get 16 lines. Carbon goes in the center, everything else goes around it. You might have put your fluorine somewhere else, and that's just fine, because remember, these molecules aren't glued to the paper. They're really moving around us. Now we need to determine the electronegativity. If you go back to your table, you can see that a carbon-chlorine bond is not going to be an equal tug of war. The chlorines pull harder, so I'm going to draw my arrows pointing towards the one who wins. And same thing for fluorine. Fluorine is the most electronegative atom on the whole periodic table. So we're going to draw that bond outward. Okay, so you have 4 polar bonds in this. Now we need to assign a term for the whole molecule. Okay, let's really think about this one. Is it asymmetrical, meaning it's unbalanced, or is it symmetrical? Is it balanced? Okay. When you look at the up and down direction, these two people are the same. The chlorine, chlorine, they're going to cancel each other out. But when you're pulling left and right, you have 2 different atoms on either side of your carbon. And so this is not completely balanced. This is a polar molecule. Simply for the fact that we have a different element here. Okay. All right, let's jump into this example. For these two, I would like you to do your math off to the side, draw your bonding picture, and then stop, and we will assign the polarity together. Okay, in this first example, I'm allowed to have 10 lines. Remember back when we were bonding, the halogens, this group here, they're only allowed to have single bonds. And so I cannot move any bonds in to make double bonds. But if I need to use all 10 lines, that means I need some extra electrons on the oxygen. So that's what this one should look like. You're going to draw your polarity arrows. And remember, fluorine always pulls really hard. So that's going to look like this. Now we need to decide if this is symmetrical or asymmetrical. And this one is pretty tricky. Okay, this one is tricky because you have to think about what shape this is going to make. And because we have these extra electrons on the oxygen, you have some lone pairs up here. Okay, and remember, that's going to push these legs down into a bent shape. Okay. This is not symmetrical. So we would assign this the term polar. It is asymmetrical. It is polar. Okay, and if you want to draw these big bubbles of electrons up there to help you see that, that might help as well. All right, and then our last example is going to be SiO2. Oxygens are allowed to have double bonds, so you should have double bonds here. And when you compare the electronegativity of silicon and oxygen, well, oxygen is more towards the top right, so your arrows should pull outward. I do think it helps to think about the shape. What shape is this going to be? It doesn't have any lone pairs on the center atom, so it's going to be linear. And when you think about a linear shape, it is very symmetrical. Both halves are the same. So this would be an example of a non-polar molecule. Okay, so hopefully that helps you see the difference. You know, you won't get super tricky ones like this on a test or a quiz, but you should be able to assign one of these terms to most molecules now that you know how to bond and how to picture the shapes in your head. Okay, this last little bit here at the bottom talks about some properties of these two compounds, these two different types of compounds. And so you'll want to read through this, especially before you do the lab this week. The lab that you guys are going to be doing with soap and milk and food coloring is one of my absolute favorites. So I hope you guys have a blast doing it, and it's a great one to do at home to show your parents and your siblings some really cool chemistry stuff. So here in your notes, I just want to give you a couple of examples. One common example of a polar molecule is water. When you draw out water, it is very asymmetrical. And then an example of a nonpolar are going to be your oily substances. Okay, hope you guys have a great week.